Hello and welcome back, and today Kickstart's part of a four-part series of videos where I want to talk to you guys about solid state drives. This technology has come forward so much in just under 20 years. We've seen solid state drives rise from this incredibly expensive, out-of-touch, business-only product to something pretty much all of us have in one form or another. In our mobile phones, in our tablets, or even in our TVs in some cases, there is solid state drives. And throughout the course of this four-part series of videos, I'm going to talk about the best and the worst. I'm going to talk about some of the brands and their own specific SSDs, and hopefully help you guys understand the right solid-state drive that you need for your task. Now, straight off the bat, today's video is about terms. There are so many words that are thrown around in conjunction with SSD marketing, be they very technical or kind of a bit buzzwordy, and you kind of hear them and go, well, that sounds like a very high number, thumbs up. And there's more to it in a number of cases. So today I'm going to go through some of the most common terms that are thrown around in the field of solid state drives to help you guys understand what they are, and more importantly, are they relevant to your storage purchase? Now, one that we're hearing more and more these days is TCO, total cost of ownership. Now, this is kind of comprised of all the other terms we're going to talk about today. The reason I want to talk about it first is whenever you look at an enterprise grade product, you see a TCO rating. And what that is effectively a number for you to decide what this drive is going to cost you. It factors in everything from the price of the drive itself to the overall capacity, the endurance, the power consumed while it's utilized, the mean time between failure, basically every single variable while this device is in operation, and works it out to a numerical figure in terms of pounds or dollars or euros. That is the TCO, the total cost of ownership. And if you're looking at small home grade SSDs, you're not really going to see that figure thrown around too much. But the minute you get into flash servers and AI and stuff like that, TCO will be thrown around. Next, we can talk about IOPS. Now, IOPS is a term that's been around again pretty much as long as SSDs. Now, SSDs have always had the inherent advantage over traditional hard drives because they don't have moving parts. Hard drives have got platters and disks and arms and actuators and all kinds of stuff reading them, whereas SSDs are formed of chips. We'll get onto that later. Now, SSDs are measured by read and write, just like any other drive. Generally, the lowest grade SSDs go for about 200-300 megabytes. But IOPS is very different. IOPS stands for Input Output Operations per Second. And what that means in real terms is how many things this SSD can have done at any given time in a second. And SSDs, because they're multiple chips being read to virtually instantaneously, their IOPS are measured in the tens, if not hundreds of thousands. You will find that read IOPS, that's accessing data, is going to be quicker than write IOPS, that's individual operations happening to a disk, actually data being written to it. But even low-end SSDs will have IOPS in excess of 10,000. The majority of enterprise-grade SSDs will have values in the hundreds of thousands of input-output operations per second. 600, 750,000, some of the top-end stuff using NVMe and some of the high-end NAND. But we'll get on to NAND now. Now, NAND is the chips. There's more to it than that, and I'm going to try and keep things as chewable and user-friendly as possible, but an SSD is comprised of very few parts. There's a connectable interface that we're going to get to in a second. That's how you connect the device. There's a board that it's on, that's just a little circuit board. There's a controller at the top, and that negotiates data with the chips and the interface at the top. And you've got the chips themselves, the NAND. And different NAND have inherent advantages and disadvantages. My next video, I'm going to focus specifically on NAND to let you guys know the difference of all the different kinds and which one's best for you. But for this video, you might as well bear in mind that there are three core kinds of NAND. There are more than that, and they're deviations of these, but they're pretty much these three: SLC, MLC, and TLC. Single layer chips, multi-layered chips, and triple layer chips. Now, as it sounds, each chip has a certain number of layers, like a CD when it was dual write and stuff like that. And it means that these NAND chips have multiple layers to them, and the data can be written onto those multiple layers, which means a chip with multiple layers holds more data. But inherently, the more layers the chip has and the cost of production will also factor into its overall durability. SLC, for example, single layer, is by far the most expensive chip to utilize and has the highest durability. However, it does have the lowest amount of capacity readily available, and its expensive nature and expensive production, particularly on a wider scale, result in SLC very rarely being used in modern NAS today. Most modern NAS fall on MLC or eMLC or CMLC. MLC multi-layer is typically 2 layers, and it means you have a better balancing point of reliability, capacity, and overall durability overall, and the price point is better as well. At the top end there's TLC. Now, TLC or triple layer chips are the most cost effective and still give you a very, very good level of performance and the very highest level of capacity. But it's worth highlighting that TLC also breaks down into 3D TLC and other things like that. So NAND is effectively the chips. Do check out my next video where I will go into a lot more detail about these three and the other kinds of NAND currently commercially available for SSDs today. Moving forward from that, we can talk about interfaces. Interfaces on SSD drives primarily come in 4 forms these days. The most basic being SATA. SATA's been around for a long time, arriving at 6 gigabits per second, or a maximum theoretical of 600 megabytes per second performance. Above that, we have another industry familiar in the form of SAS. SAS is an interface based on PCIe that arrives at 12 gigabits per second, or 1200 theoretical maximum on its SSDs. But it's worth mentioning that you will reach limitations without the build of a hard drive or SSD connected via SATA or SAS. A follow-up from that is NVMe, a PCIe proprietary connection that theoretically can go into the up to tens of thousands of megabytes per second if the technology gets there. Currently, the highest grade NVMe's give you around 5,000 megabytes per second read, with write somewhere erring at the 3,000 to 4,000, depending on the quality of the NAND and the controller you are utilizing, and of course the data. A lot of these connections are then brought together with the very top tier in the form of U.2. U.2 looks like standard 2.5-inch SATA connections, but it is a proprietary SAS external onto an NVMe build. It is the highest grade currently of enterprise level SSD in terms of capacity and speed, although at the price they are by far the highest out there. Some SAS or dual SAS connections promising 24 gigabits per second do get quite close to that, but aren't as established and certainly not as widely regarded right now as U.2 and NVMe commercially. But those are the kind of interfaces that modern SSDs will utilize. Now, why would a person use SSDs? Well, there's another key word: caching. Caching is when you are kind of assisting a system of accessing either writing or reading data with a kind of buffer area of additional fast-acting storage. Memory works like this, although memory is constantly flushed. Cache can be maintained to hold data permanently or semi-permanently, as long as the system's in operation at least, and allows data to be read and written to significantly faster than without it. It is an expensive method, and it's one of the main ways in which SSDs were first introduced into a commercial sector, used in partnership with much slower hard drives, providing an area of cache. And caching is something that we see all the time. It comes via a number of other names like buffering in different areas, and what it effectively comes to is assisting the delivery of data either in real time or lining it up for real time afterwards. Now, another popular term used in SSDs is encryption. The most common one you will read is SED, self-encrypted drives. These are SSDs that come with an area of self-encryption. All the data that are being read and written to this drive is encrypted internally. It's all done within the SSD. And that means that if the SSD is stolen without the encryption unlock key, it is useless. The entire disk is using a comprehensive algorithm to protect it from theft. And that's not the only method of encryption that's common these days, with large, particularly kind of government-backed industries using something called FIPS, F-I-P-S, and that is a military-grade kind of government use encryption system. And a lot of SSD vendors have got onto this, releasing products that are FIPS supported. So that means that a government will go, that's the drive I'm going to use for my large server array to monitor all of my citizens. Big Brother is watching. Now, these are kind of the most common terms that industry users will use in terms of both encryption and the utilization of SSDs. Home users, less so, because SSD use in home or even small business use is normally restricted to 2, maybe 4 SSDs, and you rely more on IOPS and read and write. But that's not it. You also have 2 popular terms that are thrown around: terabytes written and drive writes per day. Now, these 2 terms respond to how much data a disk can take before it is unusable. Terabytes written can often be calculated by the overall capacity times against the number of days it will be in operation, 365 in most cases at the very max, and of course how many years it's covered by its warranty, and that should give you some idea of data terabytes written. But drive writes per day is a fractional equation. With that, it gives you some idea how often you can completely fill a disk of data. So if it's a 240 gig SSD, how many times a day can you fill this drive to the maximum capacity? And the data write per day is a calculation. I always have to look off screen for this one. The calculation is the terabytes written divided by, open brackets, the warranty length, so 5 years typically, times a year, so 365 days, in other words, times by 365, and then times the overall capacity of the drive in gigabytes. That equation equals your data writes per day and is often shown as a fractional sum, with most drives arriving at the 0.3 to 0.6 data writes per day, and that is a fraction of the overall capacity of the drive. So of a 1 TB drive, 0.3 data writes per day would be 330 gigabytes, give or take. Now, more enterprise level drives, you start looking at whole sums of data write per day, from 1.0 all the way up to some cases 5 or even 10 data writes per day, with enterprise level disks allowing you to completely write an entire disk size of data per day several times. If you're working in AI operations in a flash center or data center using flash, this can be incredibly attractive. But again, home users just want to know that the data writes per day and total writes, terabytes written, are apt for their utilization, whether they're using it for caching inside a NAS drive or as their main storage drive for the OS and stuff like that, with a hard drive taking up the slack in the background. Now, we can talk about some other rather boring terms that home users know of but don't really utilize, like ECC, error correction code. And this is when data is passed through an SSD and a checksum is created at the beginning and the end of the data transmission and compared. And if in the event there has been a change, a deviation between those 2 checksums, the system will repair the data based on the previous checksum, allowing data to not suffer things like bit rot, which is more of a factor in hard drives. But with SSD and its rather disposable storage level, it is still a factor. Another rather arcane term that is thrown around, which is hard to apply to a lot of storage, and I know a lot of people don't rate it, is MTBF, mean time between failure. This is effectively a measurement of how long a device is supposed to work before it could theoretically or potentially fail, generally measured in hours or millions of hours. A mean time between failure is effectively you start using it, the number of hours that go by, and then it fails. And it is measured on the idea of a device being on for a certain period of time. How many times is it down? Now, hard drives, it's far more applicable to, because hard drives have more mechanical moving parts, but SSDs don't really have that. And as a term, it has kind of fallen out of favour in the world of solid state drives. Unsurprisingly, it's still mentioned because it sounds really, really impressive, but it has no real world grounding in modern SSDs these days. And that's really it. The only other term I was going to touch on is trim. And trim is about deletion. Now, you might hear about SSDs supporting SSD trim or devices that will utilize SSD trim. And all it means on its most basic level is when you delete something from an SSD, is the data truly deleted? Without trim, in most cases, when data is deleted, when you action a deletion, all that happens is the SSD will remove that file collection from its index. It will no longer have access to it. Think about when you format a drive in Windows and you choose between quick format and a real format. Well, without trim, it's kind of like a quick format. All you're doing is severing all the index, all the link to the data that's on there, and now it's defunct and effectively deceased. It's just there, but inaccessible, unusable, untethered. And without trim, that data will never truly be deleted until the data is being written to it with the next layer and the next full capacity of data on that disk, on that NAND cell chip. With trim enabled, or an SSD that features trim, a deletion is truly a deletion. It's a full format comparison. Data is completely removed and expunged from the disk, even without fresh data being written to it. And a lot of people that want to make sure their data is truly deleted will often seek out trim enabling on the device or on the disk itself to make sure it is supported. But this has been the most common terms used in solid state drives. There's quite a number of them, and I hope you found this video helpful. Do stay tuned for my future videos where I'm going to talk through the very best kind of SSDs from the brands that are out there, as well as the difference between all of those NAND chips. But otherwise, thank you so much for watching. I hope you found this video helpful. If you did or enjoyed it, click like. If you want to learn more, click subscribe, and I'll see you next time.